free approach. So this is a joint work with Lily from Zhejiang Constitutional University and Menzin from UC San Diego, and Wen from Colorado State University. Okay, so first we talk about a little bit about the background and motivation of this work. So we're now in the world of big data. As a statistician, we often see our colleagues assume some big assumptions when handling the big data problems. So the most common assumptions, such as the sub-Gaussian errors and no outliers, especially in the work dealing with high-dimensional data, among others. But however, in practice, big data is often big data are often contaminated by heavy tail errors and outliers. For example, so outliers is often to be found in imaging and microarray experiments, and also if we look at the gene expression data, they also often exhibit heavy tails. For example, if we're looking at this plot, which is a set of genes, set of expression of a statistically significant set of genes of human skeletal muscle biopsies of some diabetic patients. Okay, so we can see that there are a large portion of genes which has a sample proptosis which is greater than 3. So which means that there are possibilities carried out actually. Okay, then let's give some more formal definition of what is light and heavy tails we are talking about in this work. Suppose x is a random variable with mean 0. We say that x has a light tail or a sub-Gaussian tail if it has this kind of exponential concentration property. Okay, and otherwise, if we only have the x to be polynomially concentrated, we call it is heavy tail. So this is some definitions. Okay, so why does the heavy tail matters? So we just look at the simplest univariate mean estimation. Okay, so suppose we have these samples xy to xn, which are IID copies from some distribution of x with mean mu, and we want to estimate this mean. So the most commonly used estimator is a sample mean estimator, and we have this kind of classic result if x satisfies. Sorry, maybe I should use this one. If x satisfies this Laplace transform condition, we especially say that x is sub-Gaussian, and also of course is light tail, and then we'll have that the sample mean estimator have this exponential type of concentration. So using the terminology by de Broglie, we call such an estimator is a sub-Gaussian estimator. Okay. But how about if we relax a little bit on the conditions of x? So we don't assume it's lighter anymore. We just assume that x has a finite variance. Okay. Then we claim that probably we will only have a polynomial type of concentration for the sample mean estimator. So the worst case is given by Catoli 2012. It says that there exist some distributions with mean mu and finite variance sigma go, such that for all large enough t, we'll have that the probability of concentration greater than some constant c times t to the power minus 2. Okay, so sample mean turns out to be not a good estimator anymore for the heavy-tailed data. So our question is whether there exists another estimator such that it is an sub-Gaussian estimator of the mean mu. The answer is yes, actually, luckily. And also the answer has been exist for more than half centuries. So we're going back to the work of Huber. So I think he proposed this kind of laws in 1960s. Okay, the Huber laws actually is is identical to the OLS laws in the range of minus tau to tau, but will become linear outside the range. So it's an adaptation from the OLS actually. And we call the Huber estimator for the mean is the minimizer of the sum from one to n and of the Huber laws and of xi minus theta. Okay, so this is the Huber estimator. So the amazing property of Huber estimator is that it turns out to be an stochastic estimator if we're choosing tau properly. So here we're choosing tau equals to 4 times v times the square root of m over t, and then we have that the Huber estimator is exponentially concentrated as long as n is large enough. So this result is given by Fan and his co-authors. Okay. There are also other type of robust. I mean, the Huber laws. We call Huber laws and robust. I mean, using Huber laws to estimate the mean as a robust estimation. But there are other type of robust estimations. For example, there are Cauchy-Lorentz laws and also Tarski-Spelvig laws, which might have similar property as Huber laws. Also, we don't analyze the static properties of those laws here, but we do use them as a competitor in our later numerical statics.
Sorry, I have a question. So for that result, that's based on the polynomial tail distributions?
Sorry?
So this result is based on the polynomial tail distributions?
Yeah, we only assume that it has a finite variance, sigma. So that's the only thing it assumes in this theorem.
There's no tail distribution?
No.
Tail assumption at all?
No.
Okay, thanks.
So problem actually is not solved yet, because when we see that in this theorem, the tau is linked to the unknown underlying variance of x. So actually we know the order of tau, but we didn't know the value of tau actually, right? So the problem is not solved. So how to choose tau in practice is kind of annoying. So here I raise a question to the audience. Does anyone remember? So what is the most commonly used choice of tau when we applying the robust estimation? Does anyone remember? I'll give you some hint. So the default value of tau in MATLAB for the 3 different laws that I mentioned before are exact values as those values. So anyone remember? So where does these values come from? Okay, so let me give an answer. So the answer is also provided by Huber. So it's called 95% efficiency rule. So the tau is chosen to be these values such that the resulting robust estimators is asymptotic 95% efficiency as the OLS estimator when the data is normal. So when I say the efficiency is actually it's just the ratio between the variance of these two estimators. So this is the kind of empirical rule provided by Huber. And of course, if the data is heavy tailed, the robust estimation will be much more efficient than the OLS estimator. Okay, so this is the empirical rule. But of course, so this is not the way we want to do it, because as seen in the theorem, in the theorem that tau should be data adaptive, because it is changed with n, so it has to be data adaptive. So in this work, so we want to give a methodology to choose tau adaptively to the data, and which is also tuning free, which means that we don't want to include another round of complex like cross-validation or other techniques. And we want to give some strict guarantees of the proposed choice of tau, and extend the method to not only the mean estimation but also to the regression, linear regressions, both in low and high dimensions. And at last, we implement the proposed method numerically. So first, let's enter the first part. We're taking one step back. We're not looking at the Huber laws directly, but another kind of mean estimator, which is similar to Huber laws. We call it it's called censored mean approach. Still, we're assuming we have these kind of xn, x1 to xn, which are all univariate context, okay, with mean mu, and we only assume it has a finite variance sigma square. Okay, so for any given tau, which is also a robustification parameter here, so the censored mean is defined like this. So which actually is just taken to be xi itself if it's less than tau, if its absolute value is less than tau, but equal to be tau if it's absolute, equal to be minus tau or tau if its absolute value is greater than tau. Okay, so this is very simple. And with very simple some technical proofs, we can show that the censored mean itself is the Gaussian estimator by choosing tau as a similar order as in the Huber estimation scenario, so which equals to the v times n over z to the power taking the square root. Okay, we'll have that the censored mean is exponentially concentrated. Okay, so let's look at the value of this tau. So this is so the unknown value of v makes the estimator is not genuine because it depends on the unknown value of sigma, right? So our goal is to obtain a data-driven choice of tau, and which will lead us to the data-driven of the estimator. So this is what we want to do here. So a naive choice of tau actually is just using the sample version of the second moment, right? So we're using this. If we can imagine if we're using this choice of tau to mimic the V2 actually is the second moment. So this is one possible choice, but actually if we're choosing it in this way, it's not good. So we're facing some risks. We know that when x is heavy tailed, so the empirical mean does not perform as a good estimator of the mean mu, right? So there's no reason to believe that the sample version of the second moment is a good estimator of the second moment anymore. It just can be performed even worse, right? So our solution to this is we solve tau from this equation. So the intuition behind it is just like we're using a censored version of the second moment estimator. Using the censored version of the second moment, not itself. So if we're choosing tau from this function, and we let it to be the tau hat, and of course, if we're using the sample version, so it's just taking the sum over n instead of this exponential term, right? If we're using this sample version, so we can solve tau actually from this equation, right? So this is our strategy. So it's simple but very effective. Okay. So consequently, if we have this tau, then we can have this data adaptive estimator So before moving ahead, I want to talk a little bit more about like the existence and uniqueness of the solution to the equation I mentioned before. So basically, I use Qn to denote the equations the left-hand side of the equations I mentioned before. Okay, and we know that Qn equals to Gn0 on the range of y, such that the Gn y is less than Gn0. And outside this range, Qn t is strictly decreasing to 0 in t. So outside this range, so in this range, I mean, so the equation I mentioned before will have a unique solution, right? And so the only thing we need to worry about is what happened within this range. So for completeness, we just set tau equals to 0 on the range such that Gn0 is smaller than z over n. And note that z is something we don't, I mean, is also something changing with it as well. And in the theory, we always assume z grows at a slower rate compared to n. So this guy is, I mean, is less than 1, right? So the event that Gn0 less than 1 actually is an unit of the event that xi equals to 0. So if in the case that xi is continuous, so we have nothing to worry about because we have the probability that x equals to 0 equals to 0. So there's nothing to worry about. So actually in most of the cases, we don't need to worry about. There are some problems with solving the equation before. So that's something that's information I want to convey here. Okay, so then we have this theoretical analysis of our method for choosing tau. So we have this definition of constants C plus and C minus, which is of this formula. So I won't give the explicit form of P and Q here. It's just a function of tau. And so basically the theorem says that by choosing tau hat using the empiric version, so the distance, I mean, we have a ratio type of result. So the ratio between tau hat and tau minus 1 greater than some constant r is bounded by these three terms. Okay, so the last term is remember, so it's the probability of Gn0 less than z over n, and when x is continuous, so this term is exactly 0. Okay, and so actually what matters is these two terms, and c plus c minus actually it will be going to be a constant somehow, and r is the r here, so it's also constant. So the z is something that works to infinity with n, but in a slower rate. So we have this kind of bound for our choice tau, which says that it should be close to the real tau. Okay.
It's a very big upper bound though.
Sorry?
It's a very large upper bound.
Yes, it's kind of
I mean,
large.
think probability should be less than 1, and you already have.
Yeah, so we
best
have,
case is like
yeah.
4.
So I will give some remarks here. So first, if we say that so then it's going to 0, but as a slower rate of n, we have that tau is also going to 0, so which is something we already knew. So it follows that the constant, the function of p of tau and q of tau is converged to v2 square, which is the second moment. Okay, and if we're taking r to be 1 over 2, which is something we can do, then we have that c plus and c minus will converge to 1/3 and 1/2 respectively. And then for large enough n, we have with this probability, right? So which is going to be 1. So the tau hat is bounded by 1/2 of tau and 3/2 of tau. So we have this, it's bounded within this range. And moreover, if we are choosing a sequence of Rowan at a smaller order of Zn, square root of Zn. So basically, it's just saying that taking R going to be 0. Okay, we see that the value of C plus the constant C plus C minus will converge to 1/2, both come to 1/10. And in this case, we'll have that the ratio of tau hat over tau minus 1 bounded by this quantity is I mean the probability is upper bounded by these two terms here, and which makes the probability going to be 0. Okay, so this is some remarks that I gave for the results. Yeah, so it is kind of locked bound, so we can only use the ratio. Is that clear? Or you want to make some more comments on? Okay. Okay, so let's go back to the Huber's estimation again. Okay. So what I talked previously is using the censored mean, not the Huber. So if we are using the Huber, actually, so solving the Huber estimation actually is just solving the following equations, which is very similar to the censored mean version. Actually, is a censored on xi minus theta in this case, which equals to 0. So it's kind of similar problem, and we will also have again we. So this is the result we already see. So by Fan and his co-authors, we have that the Huber estimator is a sub-Gaussian estimator with tau equals to this value. Okay. So in this case, if we want to solve tau from some equations, so we propose it a little bit different. So we propose to solve tau from these equations. So the reason behind it is because it's a censored version of xi minus theta, which is theta is unknown, right? So to remove the thetas, I mean, if you want to solve this equation to remove theta, we can using this U statistics. So which actually doesn't make too much difference, as we will see in the later theorems. Okay, so we solve tau from this equation, and then we solve the Huber estimator by choosing tau to be this value, and then we can having an estimation for mu. So this is a simple two-step procedure that we propose. Okay, so we can show that if we're using this U statistics, so it's very similar to the result we obtained before. So we still have this ratio of tau hat over tau minus 1 greater than R. It's bounded by now is these two terms because we assume that x is continuous. Okay, not continuous, but we assume that p of x equals to x dash is equals to 0. So we are making that range to vanish. Okay, so this basically is the procedures we proposed to the data adaptive procedures we proposed, which will give tau and our Huber estimator at the same time. Okay. However, the procedure before can be expensive. I mean, it is very quick, but it can be expensive when n is extremely large, because in the first step we can see that the computational cost is of order n squared. So when n is extremely large, it can be expensive. So we can keep on actually we can keep on not solving the U statistics, but still using the original the original censored version. Okay, so we can so in that way we need to solve both theta and y simultaneously from these two equations, right? So actually, it turns out to be this is not complex actually, because if we observe carefully, so the first function f1, as seen as a function of v, it has a unique solution if v greater than 0, and the second equation, seen as a function of equation of theta, is also has a unique solution. So it can be solved very fast. So if we do it like in a iterative way, for example, if we start from initial value of theta, then we can first solve the first equation, then we get a value for v hat, and then we get the new value of v hat into the second equation, and then we solve theta, and then we like update it iteratively, so we can solve this system of equations very fast. Okay, so this is not complex at all. So this is then we call it an oscillating procedure, which is also very efficient. Okay, so I know some of you may have some doubts on there is an additional term z, so which is appears in the expression of tau, right? So here I want to make some remarks on z as well. So z is, z of course is also related to n, but if z is bounded, it's not if it not grow with n, we have no theoretical gain by using this kind of things. Because in that way, the tau is not in a correct order. Instead, if we're letting z grow with n, and we will have the correct order of tau, which will make the Hilbert estimation or the central mean estimation to be a sub-Gaussian estimator. So the only constraint we put on z is that it needs to be a smaller order of n, so it's not go too fast. Okay, and as we will see, both in theorem and also in the numeric performance, the choice of z actually is not sensitive. In terms of the performance of the mean estimation. So, and I want to make a final remark that in all the simulations results, so we're just simply letting z to be log n in all the experiments. Okay. Okay, so let's go into the context of linear regressions. So we will divide this section into two parts. So the first part is no dimension regression, which is like fixed dimension, and the second part is high dimensional. Okay. So if we consider the fixed dimensional linear regression, we have like this kind of model, and in the context of like a heavy tau scenario, we assume that so our assumption is putting on this epsilon. So we assume epsilon has we only assume epsilon has a finite second moment. Okay. And in this linear regression, so the Hilbert's estimator is defined as in this way. It's a minimizer of sum of Hilbert laws of yi minus xi transpose beta. Okay. Also, Fan and his co-authors have shown. They have a series of papers on like showing that Hilbert estimator is a sub-Gaussian estimator for different models, like in univariate mean regression and also high dimensional regression. So which is very nice. So if they assume that they consider random design, if they assume that the s to the power of 1/2 times x in a sub-Gaussian norm is bounded. Then if we're choosing tau appropriately in this order, okay. So as long as n is large enough, then with probability 1 minus times e to the power z to the power minus z, we will show that the beta tau, which is the Hilbert estimator of the regression coefficients, is a sub-Gaussian estimator. Okay, so how to how to do it? Now we have the data adaptive estimator for betas, but how to do it in practice? Again, we are using our procedures, which is solving these two equations. So from the first one, is actually just it's just the solution of the Hilbert laws, right? So if we have the value of tau, it's basically just solving the Hilbert laws. And the second equation actually is the equation we used to solve tau. So again, we will do it iteratively. So we start from some initial value, say maybe beta, and then we can solve v from the second equation, and then we get the new value of v into the first equation, and then we solve beta again, and then we do it iteratively. So with very, it can be solved very efficiently, and quickly we will have, when it converts, we will have the final result for beta and v.
Is a very quick explanation for why is it 1 over n minus t in the second equation?
Sorry, which one?
G2 equals. Is a quick explanation.
N minus 1 minus d. Sorry, n minus d. You mean this one?
Yeah, yeah. Is the sample size minus dimension?
Yeah.
Okay,
It's like
if it's too complicated, we can do it offline.
yeah. So I need to check it. But yeah. So I think it is correct. So it's not a typo. Yeah. So yeah. So maybe you can talk about that later.
Yeah, sure.
Okay, so then let's move to the sparse regression. So the sparse regression is just like we are no longer assuming the dimension of beta is it's fixed. Now we can assume it to be gross with it, and maybe an even faster rate of them. But we assume there is a sparse structure in the regression coefficient, which is only a very small number of betas are non-zero. Okay. So in that case, similar to that one, so what we're considering is the penalized Hilbert estimator. So which is the Hilbert laws and plus and one kind of penalty. Okay. So under this model, and his courses also have this kind of result showing that if you are choosing tau appropriately, and also letting the regression parameter lambda to be this order, we'll have that the beta is an sub-Gaussian estimator, the Hilbert estimator is a sub-Gaussian estimator. Okay, and then we also have our version of the procedures for this problem. So there's only a little bit details here. So here we are using some kind we are using a similar spirit such as the refitted cross validation, which is proposed by Fan when they used to estimate the variance. Okay, so we randomly split the data into two parts. Just simply thinking they are like of equal sample sizes to like n-half, right? And then we have some initial values of v0, and we are solving these two equations. I mean, so both of them they are just the penalized Huber estimator. So for given given v, we can solve beta 1 from this part, and beta 2 using this part. So using like half of the data, we got beta 1 and beta 2, two estimated for beta. And then we updating v by solving these equations. So we're taking account of both parts, right? And we just using the cross of it. So we see here is n1 minus the sparsity of the second beta 2 hat, and this is y1 minus x1 times x1 transpose times the beta 2 hat, and this is y2 times minus x2 transpose times beta 1 hat. So like we use them cross to make, the reason we're using this refitted way is that we want to make our application way more robust. Okay. The idea is similar to the previous procedures. Here I want to mention some on the algorithm that we are used numerically to solve the problem. So we have like three kind of problems. So the first one is we are solving tau from the equations we mentioned before, right? For that kind of problem, we are using the first position method, which is that we start from some value, and we are solving the function f2 or g2 or whatever. I mean the level of equations I did before, and our update is we consider this value, which A and B are lower and upper bound for the value of tau, and we are assuming and we solve a C from this value, and if the value of the functions which is using A or C is times, it's greater than 0, so we will letting the C to be the new A, and otherwise we are letting C to be the new B. So by this updating method, so we will solve tau eventually. So this is called first position method, which is supposed to be converted super linearly, and so it means it's super fast than the coordinate descent. So this is why we use it. And so the other problem is like solving the Huber laws. So for solving the Huber laws, there is a very common method which is called iterative repeating. So which is that we can say that the solution of Huber laws actually is like it has this kind of form. Well, Wi is a weight. So again, if we have some initial values for theta, so we can update Wi and theta iteratively. So this is called iterative repeating. So which is commonly used to solve the Huber laws. And the third type of problem is solving the penalized sparse Huber regression. So in that problem, we are using the algorithm called semi-Newton coordinate descent algorithms, which is proposed by E and Huang 2017. So the intuition behind this algorithm is that noting that the Huber laws, the penalized Huber laws problem is also convex. I mean, it's convex, and it satisfies the KT condition. So solving the beta from that equation is solving the minimizer of beta of the penalized Huber expression is equivalent to solving these systems. Okay, and to solving this system, we can do it using the semi-smooth Newton method, which will have a computational cost of order n squared times p. But instead, so in the SNCD, they propose to separate this system into two parts. So the first part is the first equation, and the second part is the last two equations. So they're solving beta 0, which is the intercept from the first part, and solving the beta hat and also the SJ hat from the second part. So they just apply them iteratively. So this will give a more cheap computational cost, but will achieve a similar performance in terms of estimation. So this is basically the this algorithm achieves. Okay. Okay, so next we are going to show the final part of my talk, which is give some numerical result showing that our method performs well. Okay, so we consider unfortunately we didn't finish all the parts of simulation yet. So I can only show you the partial results. So we're looking at the regression settings. So first, low dimensional settings. So you will generate x and y and betas from this model, where we will fix the sample size to be 500, and our beta is set to be 5. Actually, 5 is corresponding to the intercept, and we are letting the beta 1 to beta 5 equals to 1 minus 1, 1 minus 1. So in this case, d is equals to 6. Okay, and we're considering 4 different types of errors. So first one is normal, which is light out, completely light out and symmetry. And the other story, they're more screwed and heavy tailed. So it's like screwed T distribution, and log normal and parallel. Okay, so this is the distribution that we're considering in the simulations, and we're considering using ORS and also Cauchy laws, Target-Spellwick laws, and Huber laws. So both are with the default value of tau, which is I showed in the beginning of the talk. We're using the default value of tau, and then compared to using the data adaptive version of tau solved by our procedures. Okay, so this is this in this table we are showing the result of rescaled L2 error. So which is just like the L2 distance between the beta, between the beta hat and beta, and divided by the L2 norm divided by d, and then taking the square root. Okay. And we can show that in the normal case, so it seems to be no improvement at all, right? And we can see that actually, so those 3 robust expressions, they behave very similarly, and our method is slightly better, I would say, but not too much. And also in that case, ORS is the best one, right? Because it's normal. But in other 3 cases, we can see a very obvious improvement if we are choosing tau adaptively comparing to the Huber. You can see, and also those 3 guys, they perform kind of similar. So this is basically the results, and also we give in this part we are showing the distribution of the L2 arrow only for the intercept term. If we're looking at the estimation result only for intercept, we can say that in the normal case, all the 4 methods behaves very similar. They are almost the same, but in all the other 3 cases, we can see that the adaptive Huber will perform. Will have a significant improvement in terms of the distribution of the L2 arrow. Also, this plot shows the actually is the L2 arrow versus the parameter distributions, which means that we are changing the parameters of the different arrow distribution, which will affect the tails. So remember, in the normal case, what we're changing actually is the variance, and we can see that, of course, not surprisingly, so all the methods they are performed similarly. And in the screwed generality, what we are changing actually is I think is the POQ here, which will affect the fatness of the tail. Sorry, we can see that as it so which will affect the degree of freedom. Actually, is similar to the degree of freedom in the student's T, and we can see that as it grows larger, which means that the tail is getting lighter. Again, we can see that the methods mean the L2 arrow will decrease, but I mean, again, the data adaptive humor is performed uniformly better than other methods. Okay, and this is the log result, and this is the Pareto results. We can see that in all cases there is a significant improvement of the data adaptive version. And in the high dimensional regression case, we're considering these settings of beta, which is informed to be 3 for the first 21, and actually it's like the intercept plus the first 20 of beta. And to compare to compare our method, we are comparing to the directly using the Natsun estimator, and we're compared by using this relatively L2 arrow, so which is a ratio between the Huber estimator and the Natsun estimator. Okay. And also the other quantity we are comparing with is the number of false positive discoveries. False positive means that it is 0, but we choose it. Okay. For the reason we didn't mention the false negative discoveries, because the signal is kind of strong in this case. So the false negative discoveries are almost 0. I mean, for all the methods. Okay, so we can see that. So here the type 2 and type 1 and type 2 DA actually means that the two different ways we are using for cross validation. So I will not talk about them in detail here, but we can see that it turns out the data adaptive Huber estimation have a very significant improvement in terms of the false positive discoveries. Well, we know that the term is best. I mean, especially when the dimension is high, it turns over select more variables. But if we are considering the Planet Huber, it will significantly improve the model selection effect. And also, if we're looking at the relative L2 arrow, it will give an improvement as well. Okay. So that's basically what I'm going to talk about today. So here is a brief summary. So what we did in this work actually is we successfully choosing tau in a Huber estimation in a data adaptive fashion, and we give a tooling-free approach to compute directly. And we extend this method to regression settings, and we develop the algorithm to implement the proposed method. So that's basically what we did, what we have done. So thank you. and references.
Any questions?
So in terms of the theory, you have results on how, say, mu hat tau performs for a fixed value of tau, and then results on how you can estimate the optimal choice of tau.
Yeah.
Is there any way of combining those to give results on the performance of like mu hat, tau hat, so the sort of the data-driven choice?
The mu hat, tau hat.
Yeah.
You mean the theoretical results?
Yes.
Yeah, I think that should be possible. I mean, as long as you can show that tau is in the correct order, then we have this kind of exponential concentration, right? So I think it's not too hard to do it, right?
But I guess you have to do some data splitting, otherwise don't get independence. These two events.
Yeah, that's true.
I actually have a question about your data splitting. So what did you gain from doing data splitting?
So actually, from the numerical results, we can see there is some slightly gain in some of cases, which one I forgot, but in most cases there is similar to not using the data splitting. But maybe one or two cases is perform slightly better. But if we are not using the data splitting, it still has a significant improvement comparing to the Zoom.
So it's just for the numerical thing,
Yeah.
not
Not
for theoretical.
for theoretical.
In your first setting, how crucial is the condition of finite variance?
Sorry.
In your first setting, this estimation of mean,
That's
you assume the variance is finite.
Yeah.
Without that, what can you say?
Without that, yeah, that's a very good question.
You know what I was thinking? Because when you estimate the mean, you have the finite variance, the estimated asymptotic norm. I noticed a significant improvement in your numerical comparison. But you always use a very skewed distribution. If you just have it tell symmetrical distribution, the improvement wouldn't be that big.
Yeah, I suppose that is the case.
So what
Yeah.
happens is if you estimate mean, but you don't have finite variance, in this case, the least square estimate may perform much worse. When you do this robust version of estimate, improvement could be more significant. You see, this is more sort of relevant in the context. I'm not saying you should work on that, on the gauge estimation. Over there, the finite variance condition equivalent to, say, the force moment of innovation is finite.
Mm-hmm.
In practice, this is a question. Yeah, but then people don't use robust version in the gauge context because there's no natural sort of this loss function to minimize. People always use the maximum likelihood estimate. Although with the second moment finite, you can prove the Gaussian MLE is asymptotic normal. But we know when the innovation don't have third or fourth moment, estimation error is bigger. I just wonder whether there is manage to push into the direction. Say, in the first case, you estimate a mean, the variance is infinite.
Okay. So we didn't think about that in the theoretical. As a theoretical consideration, because our theoretical support is from Fanswork, so which is basically the finite second moment is a very basic support. Yeah, so it's worthwhile to invest more about that. Yeah. And also in the numerical, I think we have made something. We have made some experiment in the student team, so which is actually symmetric. But in that case, is, I mean, the improvement is also not negligible. I mean, there is we can see a significant improvement as well, at least in the numeric improvement in the numeric statistics.
And you should include it in the paper, otherwise.
Yeah,
when
so
say
it's
regression
like
improvement
we are giving
Yeah.
I mean we are making trust between the security or stability. So we pick the latter one. Yeah, it's a good statistic. We may need to repeat the T as well.
If there are no more questions, we'll just thank Chao again. I think our next talk is on Thursday.